All right, so our next talk is on quotient polymorphism, and I should note that this is a Distinguished Paper Award winner, and Brandon Hewer is going to be giving the talk.
Okay, great. Okay, this is working. Okay, good. Okay, so I'm going to begin talking about exactly what kinds of quotient types I'm talking about here, and perhaps some of you haven't approached quotient types before, and I imagine some of you have. So let's begin with that. Okay, so I'm going to be doing this in the syntax of a system called Quotient Haskell, which is a system that I'm developing. It develops on top of liquid Haskell, so it's designed to integrate on top of a refinement type system specifically. So this means we have this predicate-based refinement typing from liquid Haskell here that I'm going to compare quotient types with. So I've got two different definitions here of the natural numbers, one via subtype, which probably is readable to most people here, hopefully. It's just the integers that are greater than or equal to 0 here. And the second one is perhaps a little bit less familiar to some people, and that's defining the natural numbers as a quotient type. And it might not be immediately obvious, although to some of you it will be, what this says, but it just says that I basically need to be invariant with respect to sign, that I can't use sign information when I use these natural numbers. So in other words, any function must send both the positive form of a number and the negative form of a number to the same value. Okay, yeah. So I'm going to be using different terminology through this talk. So we have these things called predicates and refinements. Actually, we won't be talking much about these in these talks because we're going to be moving on to quotient polymorphism, so we're going to stick to the quotient stuff later on. But in the second thing, I've called this here equations/quotients. Actually, eventually these things I'm just going to be calling equality constructors, which is a common name in type theory. So, okay, so to take a look at the difference between these two different types of natural numbers, for the subtyping version, on construction of a subtype, you have to give a proof of the predicate that you have here, or the subtyping condition. So the subtyping condition is a proof that you give on construction. So what this means is this won't type check, for obvious reasons. If I add two integers together, I'm not necessarily going to get a natural number. So this obviously doesn't type check. Okay, but on elimination, so if I have a natural number and I want to get back at an integer, that's just free to do, essentially. Because, well, in this sense, every natural number is an integer, or at least there's an embedding, right? Okay, now let's take a look at the opposite side of things for quotient types. So for quotient types, we get a bit of a duality going on here. So on construction, and this might look, it might feel a bit strange, it might look a bit strange, but if I add two integers together here, this type checks. This is perfectly fine. Adding two integers together gives this form of natural numbers. And that's because I promised that on elimination, so whenever I use these things, that I can't just be trying to extract back out again. This doesn't type check. And this doesn't type check because it's not necessarily the case that I'm sending the positive and the negative integers to the same thing. Okay. So Quotient Haskell actually implements a form of quotient types known as quotient inductive types. And it does this in a little bit of in a different way to those of you who are familiar with things like cubical algebra, because in this sense, we actually cannot introduce new data. We're building a refinement type system here, so we actually can't introduce new data constructors. So all we can really do is refine existing data definitions. So what Quotient Haskell does is it treats inductive definitions, like the definition of a list, as its shape functor, essentially. It treats it like its shape functor, and it overloads the types of the normal data constructors, and it infers which one you mean by application, essentially. So, okay, so here we have the definition of bags. So this is just a quotient on the lists that says that I can, well, it has to be invariant with respect to permutations of the list. So these are also just called multisets. In this case, we're actually talking about finite multisets because Quotient Haskell has the restriction at the moment that you can only talk about inductive types. There's no co-induction stuff going on here. So we're going to assume everything is inductive, and liquid Haskell has a form of termination checking to get this stuff off the ground, and strict positivity checking is going on here too. Okay. Yeah. So the important thing here is these actually are quotient inductive types, and the reason is actually you're kind of introducing the data constructors here. So as I said, when you give these things called the underlying type, you're actually introducing new data constructors here. And then simultaneously, you define the equality constructors alongside them. So this means the equality constructors can have inductive references to the quotient type that you're currently defining. This would be a different type, in a sense, if instead of putting bag A here, you put list of A here, because then it wouldn't be true inductively. It would only be true on the head. So you can only switch. You'd only need to be invariant with respect to the first two elements if you put list here instead of bag. It's not necessarily the same thing. Okay, so another thing to mention is that you can build hierarchies of quotient types. So if you've already defined bags, you can go ahead and define sets. And you can define sets as what looks like a quotient on bags. What goes on here is, again, it finds out all of the underlying data constructors. So it finds out the underlying shape of the data structures of the underlying type. Replaces all of the inductive occurrences here with set instead of list. And then it does the same thing again for the equality constructors. And this means we get the kind of normal definition here for finite sets that you'd expect if you're going to write down a quotient inductive type in, say, cubic lambda. But this is all being done in a refinement type system where you can't actually define the new data structure simultaneously. And of course, something to mention here that's quite interesting is this gives rise to a natural hierarchy of surjections here. And in Quotient Haskell, these surjections are implicit coercions in the type system. So from an intuitive perspective, this isn't actually quite true because they're surjections, not embeddings. But you can think of it as being something like every list is a bag and every bag is a set. So if you have a list, you also have a bag. Okay. Yeah, so as I mentioned, Quotient Haskell is an implementation of quotient inductive types. They can be freely composed in all the ways you'd expect with the liquid types in the system. You can add liquid types into the definition of equality constructors. You can take refinements of quotients, all of this sort of stuff. Yeah, and so in a similar sense to liquid Haskell, the proof obligations that are created by the respectful theorems are generated by quotient types. When you actually use them, they're discharged to solvers, things like the proof by logical evaluation system and SMT solver. Okay, so that covers the basics of the quotient types implemented by Quotient Haskell. So now I'm going to get into the problems that we're going to address now with the current system. And then we can get straight into the quotient polymorphism stuff. So why do we even need quotient polymorphism? Well, let's take a look at the two problems. First of all, if we take a look at these three functions here, you'll notice that these three functions, if I define them on things like sets and bags, they're going to have the same definition for the two different types. At least their definition on data constructors is going to be identical. And in Quotient Haskell, the only definitions you're really writing down are the data definitions, essentially. But at present, if you want to be able to have a map function for bags and a map function for sets, you'd have to write separate ones. Because here, actually, the lists appear. You have a list in a covariant position and a list in contravariant position. So subtyping isn't going to do it for you here. So you need some form of polymorphism to avoid duplicating the definitions of these things. I'll get into them. OK, and then the other issue is expressivity. Again, if we were carrying proof witnesses with us everywhere, say if you were taking like a setoid style approach to quotients, you're carrying proof witnesses, you could do something like this. It gets a little bit more tricky in this context because, again, we don't have the proof witnesses on us, or we don't have them. We just have to deal with the proof obligations at the point of the refinement type system. OK, so in this case, the isMember function, if we refine the type of count to work on bags, which is fine. Count function on multi-sets is perfectly fine. We cannot then go ahead and refine the, oh, it's kind of, I guess it's slightly off the screen. Yeah, OK, yeah. Yeah, we cannot quite refine the type of the isMember function to this on sets, right? This doesn't work because if we take the set, we're then going ahead and trying to pass it through into the count function, and the count function doesn't allow us sets. This is a bit of a contrived example because you probably wouldn't define an isMember function this way, but it's just here as a very simple way to illustrate the point that even though this is, in a sense, a valid, even though the isMember function is really a valid function, depending on how you look at it, on sets, we cannot define it this way. And more generally, if you're kind of breaking down quotient types and you want to use them, you're kind of doing something locally that's not necessarily well behaved with respect to the quotient, but you fix it later on, there's no way to kind of detect that in the current system. Okay, so to address both of these issues, both of the code reuse and the expressivity issues, we introduce this notion of quotient polymorphism. Later on, I will also call it choice polymorphism, which is a specific type of quotient polymorphism. I use that terminology because there's different ways you could approach quotient polymorphism, and I gave a specific name to the one that we came up with. So I'm going to split this into 4 parts. The first part is typing for quotients, which I really should have called this typing for quotient, well, this is fine, but typing for quotient variables, essentially. The quotient variables that we're going to quantify over later on, they're going to need a specific type. So the fact that universal quantification is not enough, to many people, this would already be blatantly obvious, and perhaps when you see some of the slides in a moment, it will also become blatantly obvious. Most functions, for that matter, don't respect or aren't compatible with all quotients. That would be, yeah, that would be nonsense. Okay, then I'm going to introduce our notion of choice polymorphism, that's what it actually is. And then finally, I'm going to talk about a few examples of choice polymorphic functions in practice. Okay, so in this sense, polymorphism for quotients implies some form of quantification over quotients, but we need to think about kind of which quotients we're going to be quantifying over and how we kind of narrow the scope of quotients that we're actually talking about. So for example, let's take a look at this map function. It's a bit of a pseudotype here. And I've said sort of for all quotients Q, and then I've quotiented the input list and I've quotiented the output list by Q. But what on earth here even is Q? What do I mean by Q? In some sense, I mean sort of a set of equality constructors. So I sort of mean some sort of set of quality structures, but then I want to refine that further because you can see that my input list is a list of elements of type FA, and the output list is a list of elements of type B. So what on earth should this Q be? In some sense, we need to give this a type, and it needs to be able to work for either of those. Yeah. Okay, so I'm going to use a bit of shorthand here. I use this in a few different places. I've said exactly what it means. So I basically just use the normal types from Haskell here to type these things, sort of first order polymorphic types. And so Q here is actually this type for all a list of A. And all this means is that the equality constructors here have to be parametric equality constructors. And that means that the equality constructors themselves cannot depend on the type of element stored in the list. So we've already seen examples of this. The commutativity equality constructor and the idempotent equality constructor are both examples of this. I think immediately on the next slide, I believe. Yeah, there we go. This is an example of something that isn't a parametric equality constructor here. So you wouldn't even be able to apply map to something like this. It doesn't necessarily make sense to do it either in this circumstance. And that is this one. I mean, this is because it literally inspects or it actually uses the element 0 here. This is specifically only an equality constructor that makes sense here for integers. Okay, so this type immediately is actually nonsense because filter, of course, doesn't work for all quotients, but I'll get to that in a moment. But this is giving another example of a type of a quotient variable that isn't just a parametric, quotient. And that's because in this circumstance, the input and output lists have the same type, and we can be more specific. In this circumstance, actually, this makes the type itself more general. And that is because you can always instantiate a parametric equality constructor at a type A, at a fixed type A. So actually, what this means is that when we compose these quotient polymorphic functions, their types of the quotient variables actually get anti-unified, whereas we're doing unification for computing the substitution of the variables to quotients themselves. So the substitution of variables to quotients we perform using unification, but for their types, we need anti-unification. So we want the least general generalization here. Okay. So for a map, I mentioned this briefly before, and for map-like functions, map-like. I'm being a little bit general here and a bit broad, a little bit non-technical. But for map-like functions, actually the universal quantifier is enough, and this is just kind of the parametricity result. It's pretty much exactly the parametricity result in this circumstance. And map will respect any sort of quotient, any parametric quotient of this form. But for any other things, such as the filter function we just saw, I'm implicitly leaving off the choose quantifier. You can do this in Quotient Haskell. These quotient variables get inferred for you, and it'll pick the least generalization for you. So that's exactly how these Q variables get inferred. So for example, for filter, the type of Q is going to be list of A, and for concat map, it's going to be type for all A, list of A. So yeah, for all of these functions, they do not respect all quotients. And you can see in the last example here, I've actually got an example where I'm using do quotient variables, just an example that you can actually use more than one at once. And I'm quotienting lists and I'm quotienting tuples in that circumstance. Okay, so if it's not enough, then we need some sort of new form of quantifier, sort of a quantifier that's a little bit more specific. We need a quantifier that says something a little bit different than just quantifier over all quotients. In some sense, I want a quantifier that says something like quantify over only those quotients that this definition is compatible with when I substitute the quotient in for the quotient variable in its type, something like that. It needs to be a much more specific form of quantifier. And that's exactly what this choose quantifier does. It does a little bit more than that too. I'll get into that in a second. So for filter here, we can give it this choice polymorphic type, where I quantify over these quotient variables, over this quotient variable Q. And so something to note that's quite important here is I can match the induction principle for these types that are quotiented by a quotient variable reflects directly the induction principle that you'd get for the underlying type, except again, you're looking at the kind of newly generated data constructors where the old inductive occurrences are now replaced with the quotiented type. So in this circumstance, the XS here in the third line actually has type list of A quotiented by Q. And we think of these quotient variables as being corresponding to some sort of set of equality constructors. They're a set of generating equality constructors. Okay. So what does this choice polymorphic function actually do? How does it work? Well, when you construct things, no respectfulness checks are done. Essentially, you're just doing the normal checks that you would do for any other functions, just normal type checking, essentially. And only at the point that you actually instantiate at a concrete quotient, not at another quotient variable, things just get passed through. When you eventually pick a concrete quotient, then you generate the necessary respectfulness terms. And of course, you do some obvious naive caching and stuff so that you're not constantly regenerating the same respectfulness terms that you've already looked at before. So I mentioned this a bit earlier. So when you compose them together, when you compose different choice polymorphic functions together, the types of the quotient variables get anti-unified, and the unification of quotient variables getting mapped to quotients themselves, that's just a normal unification procedure. Okay, so this is an example of composing two together. So if I want to compose concat map with drop first, I get, well, this is actually an application, but it's the same idea here. So if I apply concat map here to drop first, you can see that you get this new type here. And what I've actually done is I've performed an anti-unification procedure on this top type and the second one. And the top one is actually more general type, so you end up picking this one in the end, if you'd like. So basically, if you get these kind of if you ever get stuck in one of these parametric things, you kind of get stuck there eventually. Okay. Yeah, and again, we didn't actually have to generate any respectfulness terms here because we never picked a concrete quotient here. So all that's really being done is checking the compatibility of the types of the quotient variables. And that's all. Okay. However, these choice polymorphic functions can go wrong. There is a way of making them ill-type at the point of definition. You can't go ahead and pass something, or you can't pass something that's quotiented by a quotient variable to a concrete quotient. So in this example, the polymorphism, we have this input function where its second argument takes sets, and we've tried to pass to it a list quotiented by the quotient variable q. So this would be ill-typed. You can't do that. You have to go ahead and pass it to either another choice polymorphic function that you've already defined as choice polymorphic, because you need to know how the quotient variables get passed through, or you can match on it. Okay, so I'm now going to revisit an example from earlier in the talk, this isMember function, defining isMember by means of the count function. This is actually now possible, where it wasn't before, because now we're actually, when we first define count, and when we pass and we define isMember, we're actually not generated any respectiveness terms at this point in time. So we've not done any checks for the quotients because we've not actually picked any concrete quotient and concrete collection of equality constructors to check at this point. However, we still cannot go ahead and apply count to sets, because the minute we apply it to sets, we're immediately picking a concrete quotient, and suddenly count doesn't respect the IM equality constructor, so it will fail. You'll get a type checking error. But for isMember, we actually now can apply it to sets, because the respectiveness term you generate, you don't generate it for all of the local functions. You generate it for the top function at the end. And so the respectiveness term that you actually end up generating is just this one here, written down here. And this one does, in fact, hold. So this works perfectly fine. So now the isMember function can be defined this way, and this is perfectly fine when you make all of these things choice polymorphic. Okay, so a little bit more of an involved example here. We're looking at this map_accum_L function, and we're considering this kind of costed types. This is what this costed type says, is these are tuples where the first elements are integers, and where you cannot use the integer component to change implementation behavior. This doesn't make the first integer useless. It can change it can't change the resulting value. So this integer actually isn't useless, because it can do things like, for example, pick between two different sorting algorithms. It gives the same output for the same input. As long as the outputs at the end are the same, these integers can actually be used internally to change implementation details. So what this costed function does is it holds this integer that can be used to modify your program internally as long as the end result is the same. And we have this kind of map_accum_L function here, and I've quantified over the two quotient variables here, and I've made them explicit. And we can actually instantiate map_accum_L at the costed type here. This matches with this quotient variable q here, because if you notice, the second component is indeed parametric, which is what the quotient variable q requires. It requires the second component here to be parametric, whereas the first component can be any fixed type S. And if you instantiate it costed, the property that you have to have is that the input function, or the accumulation function here, doesn't use the cost, doesn't actually use the S value, the cost value, to modify the if you actually take it all into account, because the Q here, you're actually going to be producing this kind of accumulation function is also going to be quotiented by ignore cost. You can't change the internal, or the second component of this tuple, the B. You can't have that depend on the S value, or the integer here. Okay. So actually, that's kind of now right at the end. So the developmental implementation for Quotient Haskell is available online at this GitHub, and that is kind of the end of the talk. Thank you.
Questions, and could I ask the next speaker to come set up?
Thank you for the nice talk. More than a question, an observation. This recalls me a lot how you encode the bounded quantification with intersections. So instead of saying for all alpha smaller than t, you do for all alpha, and then you replace alpha with alpha intersection t. And then, in particular place, you use the intersection to check the body, but just at the application, you check whether the bound is correct, which seems to me a lot what you do. Instead of intersection, you use the slash symbol. So I wanted to know if there is any relation, or just a stupid observation.
There's a pretty heavy relation. I mean, maybe this would be good to talk about at some point. I mean, there's a discussion in the paper that goes into this too. I mean,
didn't read the paper.
I mean, the delay feature of this, where it pulls it up, is this is similar to intersection types too, right? Yeah. In this circumstance. Yeah, I didn't necessarily consider intersection types for a whole bunch of the reasons. I'm not sure how well they perform on performance and stuff. I'm not sure, but yeah. Okay.
We'll do one more question. I think there.
Thanks for the talk. It was very interesting. So if I've understood correctly, this choice quantifier is somehow a restricted universal quantifier, but only over quotients that are compatible with my definition.
Yeah, you can think of it as kind of similar to an ad hoc polymorphism thing for quotients.
Right, yeah. So I was kind of wondering how we can understand the choice quantifier as separate from the term that it's trying to type. So if I have a term in mind, I kind of know what it means, but is there... What does it mean for, what are the inhabitants of this choice type in general, if it's so tied to the term, if that makes any sense? So like for a normal quantified type, I can...
Because you don't have to necessarily give the same, so you don't have to give the same definition a single choice boundary for a type. There's several that could work for it, right?
Right, yes, of course, but I guess what I mean is I can understand a universally quantified type independently of the terms that have that type, perhaps, as I can pick. I don't know if I've got a sort function.
This is true for the choice polymorphic type too, sure. It's absolutely true in this case.
But isn't the range of the quotients tied to the term that I'm typing?
In the interest of time, could I ask for this to be cut off so we can start the next talk? Yeah, all right, sorry, thanks.
Thank you.
Let's thank Brendan again.